Hello class, this is Ms. Riggins with today's video on sections 3.9 and 3.10, Linear Approximation and Theorems About Differentiability. As you're watching the video, please write down any important notes, equations, formulas, statements, and graphs, or questions that you have in your notes, and feel free to pause, rewind, or replay the video as often as you need. At the conclusion of watching the video, write down a brief summary about what occurred in the video in your notes, and then submit that summary as well as the top question via the online quiz the day before class. Okay, let's begin. If you recall, a tangent line is a line that is tangent to a function at a point. And we used it to represent the derivative, but actually we can use it in another way as well. And that is as a way of basically approximating the function. Now in this case, you have this function here that looks kind of quadratic. And then you have the tangent line, which is a linear graph that is tangent exactly at the point, in this case, C, comma, f of C. Okay, so the tangent line, we're going to use that as an approximation of the original function. And sure enough, it's only really a wonderful approximation at the point C, comma, f of C, because that's when the function values are the same for the graph and the line. But as you get further away from C, then what happens is that your tangent line no longer becomes such a good approximation of the graph. Another example way of looking at it is this case. Instead, here we still have a true value of the function values, and then we have the line that approximates it, which is a linear approximation. And as x minus a is bigger, the error between, or the difference between, the actual function value and the tangent line approximation becomes bigger as well. And so that's what we want to take a look at. The error in this case is basically defined as the difference between the function value at a point x and the tangent line approximation at that point x. So that's the difference. And we can represent any point on this line, on the tangent line approximation, using the derivative of the function at the point, in this case a, times the difference of x minus a. And so therefore now we have a quantifiable thing that we can use to express. So if I have a function that's differentiable at a point a, then for values of x near a, and that's important that we know that it's only near a, then the tangent line approximation of f of x is the tangent line, which can be written as the f of a plus f prime of a times x minus a, where this is the equation of a line, and the slope of the line is basically the derivative of the function at the point. X minus a is, again, this is kind of like in point slope form, where you have the points a, comma, f of a, which is what we know. And this only works if f is differentiable at a. If f is not differentiable at a, then we cannot use a tangent line approximation, because we don't have a tangent line approximation. We don't have it. So anyway, we call this expression the local linearization of the function f near x equals a. So this is the local linearization of f, where a comma f of a is constant, as well as f prime of a. Now the error in the approximation is the difference between the actual value and the approximation value. Okay, so in this case, oops, sorry, didn't finish doing that. And that's how you compute the error. All right, so why is this of any importance? It's important to know because if we ever want to approximate a function, we can easily do it with a linear approximation. Now, the linear approximation may not be a good approximation, but we do know how to do that approximation. All right. We have a theorem here which says if f is differentiable at x equals a, then error, e of x, which is the tangent line approximation, is of course this. Then we can say that as x gets closer to a, then the ratio of the error divided by the error in the function value, the difference in the function value divided by the difference in the x values equals 0. And that makes sense because as we get closer to our value a, as x gets closer to a, you notice that f of x is going to be equal to exactly f of a as x gets closer and closer to a. Okay, so that's kind of obvious. If we were to take the second derivative of the function at that point a, then we can actually give an approximation of the error function using the second derivative. And we'll look at that more when we get into Taylor series, okay? All right, so that's basically it that you have to know about this section. You have to know how to determine the tangent line approximation or the local linearization, and you have to know how to determine the error function as well. And it only works if, again, f is differentiable. All right, moving on to theorems about differentiable functions. And this is a very important theorem in calculus called the mean value theorem. And some of you may be like, this is obvious, and we probably have used it before, but you just didn't know it was the mean value theorem. So let f be continuous on some interval, closed interval, and let f be differentiable on the open interval. Then there exists some point in that open interval from a to b where the derivative of f at that point c is equal to basically the slope of the secant line between the endpoints. And if that's the case, then we can rewrite f of b minus f of a as equal to the derivative at that point of c times b minus a. It looks very much like the linear approximation of something. Graphically, what does this represent? This is basically saying if you have a function that's continuous on a closed interval a to b and differentiable on the closed interval, an open interval a to b, that there is some point c in that interval from a to b such that the slope of the tangent line of the function at c is also equal to the slope of the secant line between the interval endpoints. That's exactly what it means, and this picture is a good example of that. And if that's the case, then there's a lot of different results that we can get from it. So let's take a look at those results. Now here's a graphical representation of what we're talking about, and that's for the mean value theorem. The slope of the secant line is going to be equal, of the endpoints is going to be equal to some slope of the tangent line at some point c that's in that interval, and this is a good graphic for that. There's an accompanying theorem or related theorem called Rolle's theorem, which is very similar to mean value theorem, but in this case, f of a equals f of b. And so that means that there is some c value such that since f of a is equal to f of b, the slope of the tangent line is going to be equal to 0. Since the slope of the secant line is equal to 0, there is some value c in this interval such that the slope of the tangent line, i.e. the derivative of the function at that point, is equal to 0. So the graphic really does, to me, help explain and understand what it means. And there are proofs out there that you can take a look, but I really want to take a look at the resulting theorems that are based off of that. So it says if you have f being continuous on the closed interval a, b, and differentiable on the open interval a and b, if the derivative of f is positive on a to b, then f of x, then f is increasing on the closed interval a to b. I know some of you are like, well, that's obvious because the first derivative being positive means the rate of change is positive, da 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 da. Well, this is you can prove this using the mean value theorem. And on here, if f of x is greater than or equal to 0 on a to b, then f is non-decreasing on the interval from a to b. And that's because if the derivative is equal to 0 at any point in their interval, we can't say it's increasing, but we can say it's not decreasing. Again, some of you may be saying that's obvious, we already know that, but we can prove that using the mean value theorem. Another offshoot is the constant function theorem, which says, again, we start off with, suppose f is continuous and differentiable. If the first derivative of x is equal to 0 for some x in between a and b, then f is constant. Not for some x, for all x, then f is constant on that interval as well. Sorry. So again, obvious, but we can prove it using the mean value theorem, and you will in class. And this last thing is called the racetrack principle. And the racetrack principle, and the idea and the reason why they call it racetrack principle is, let's say we have two functions, g and h, where one is always greater than the other one. So if we start a race where g and h are at the same starting line, and as soon as time goes, g of h will always be bigger than h of x. G of x will always be bigger than h of x because of that. So that's essentially the idea behind the racetrack principle. So it says here, let g and h be continuous on the interval and differentiable. There you go, on the open interval. Then if the first derivative of g of x is less than, if the first derivative of g of x is less than the first derivative of h of x for all x in the interval, then that tells you that if g of a is equal to h of a, then that means that h of x is always going to be positive, greater than g of x, or equal. And if g of b equals h of b, then that means that g of x is always going to be greater than or equal to h of x. So depending on the endpoint, that this is where they're starting at the same point, then that means that since h of x has a derivative that's larger than g of x, and that means that the rate of change of h of x is always larger than the rate of change of g of x, which means that h of x will always be bigger than g of x when they start at the same spot. And if they end at the same spot, then that means that g of x must have been bigger than h of x. I know, confusing, but just be familiar with these theorems so that you'll be able to use them in the future.